Instruments. Objectives. You will be able to 1. Sketch the construction of a permanent magnet moving coil, PMMC, instrument, and explain its operation. 2. Show how PMMC instruments are used as galvanometers, DC ammeters, DC voltmeters, AC ammeters, and AC voltmeters. 3. Calculate appropriate shunt and series resistance values for given ammeter and voltmeter ranges, and determine instrument accuracy. 4. Sketch and explain the operation of series and shunt ohm meter circuits. Explain ohm meter scale shapes, and determine ohm meter accuracy. Sketch the front panel and scales for a typical volt-ohm millimeter, VOM. Explain function and range selections, and discuss the use of the VOM. 6. Sketch and describe the construction of an electrodynamic instrument, and explain its DC and AC operation. Show how an electrodynamic instrument may be used as a voltmeter, an ammeter, and a wattmeter. Introduction. The permanent magnet moving coil, PMMC, instrument consists basically of a lightweight coil of copper wire suspended in the field of a permanent magnet. Current in the wire causes the coil to produce a magnetic field that interacts with the field from the magnet, resulting in partial rotation of the coil. A pointer connected to the coil deflects over a L-calibrated scale, indicating the level of current flowing in the wire. The PMMC instrument is essentially a low-level DC ammeter. However, with the use of parallel connected resistors, it can be employed to measure a wide range of direct 29 current levels. The instrument may also be made to function as a voltmeter by connecting appropriate value resistors in series with the coil. AC ammeters and voltmeters can be constructed by using rectifier circuits with PMMC instruments. Ohm meters can be made from precision resistors, PMMC instruments, and batteries. Multi-range meters are available that combine ammeter, voltmeter, and ohm meter functions in one instrument. The electrodynamic instrument is similar to the PMMC instrument except that it uses stationary coils instead of a permanent magnet. The most important application of the electrodynamic instrument is as a wattmeter. 3-to-1 permanent magnet moving coil instrument. Deflection instrument fundamentals. A deflection instrument uses a pointer that moves over a calibrated scale to indicate a measured quantity. For this to occur, 3 forces are operating in the electromechanical mechanism, or movement, inside the instrument: a deflecting force, a controlling force, and a damping force. The deflecting force causes the pointer to move from its zero position when a current flows. In the permanent magnet moving coil, PMMC, instrument, the deflecting force is magnetic. When a current flows in a lightweight moving coil pivoted between the poles of a permanent magnet, figure 3-1a, the current sets up a magnetic field that interacts with the field of the permanent magnet. A force is exerted on a current-carrying conductor situated in a magnetic field. Consequently, a force is exerted on the coil turns, as illustrated, causing the coil to rotate on its pivots. The pointer is fixed to the coil, so it moves over the scale as the coil rotates. The controlling force in the PMMC instrument is provided by spiral springs, figure 3-1b. The springs retain the coil and pointer at their zero position when no current is flowing. When current flows, the springs wind up as the coil rotates, and the force they exert on the coil increases. The coil and pointer stop rotating when the controlling force becomes equal to the deflecting force. The spring material must be non-magnetic to avoid any magnetic field influence on the controlling force. Since the springs are also used to make electrical connection to the coil, they must have a low resistance. Phosphor bronze. is the material usually employed. As illustrated in Figure 3-2a, the pointer and coil tend to oscillate for some time before settling down at their final position. A damping force is required to minimize, or damp out, the oscillations. The damping force must be present only when the coil is in motion, thus it must be generated by the rotation of the coil. In PMMC instruments, the damping force is normally provided by eddy currents. The coil former, or frame, is constructed of aluminum, a non-magnetic conductor. Eddy currents induced in the coil former set up a magnetic flux that opposes the sent oil_motion, thus damping the oscillations of the coil. See Figure 3-2b. BTE. Two methods of supporting the moving system of a deflection instrument ACE illustrated in Figure 3-3. In the jeweled bearing suspension shown in Figure 3-3a, the pointed ends of shafts or pivots fastened to the coil are inserted into cone-shaped cuts in jewel, sapphire or glass bearings. This allows the coil to rotate freely with the least possible 0 electromechanical instruments chap. 3 field conductor. Flux. A. The deflecting force in a PMMC instrument is provided by a current-carrying coil pivoted in a magnetic field. Scale. Pointer. Contrajalin, 2. Force. B. The controlling force from the springs balances the deflecting force. Figure 3-1. The deflecting force in a PMMC instrument is produced by the current in the moving coil. The controlling force is provided by spiral springs. The two forces are equal when the pointer is stationary. Seconds. 3-1. Permanent magnet moving coil instrument 31. Pointer. Oscillation. Pointer. Oscillation with I no damping. MO of final. YO 14. Pointer. OU4 of position. MPA4. SEUEA. NWEGs. WIS. Utni pointer / position with damping. Time. A. Lack of damping causes the pointer to oscillate. Aluminum. Coil former. Damping. FCRCE. J motion. Damping. Force. B. The damping force in a PMMC instrument is provided by eddy currents induced in the aluminum coil former as it moves through the magnetic field. Figure 3-2. A deflection instrument requires a damping force to stop the pointer oscillating about the indicated reading. The damping force is usually produced by eddy currents in a non-magnetic coil former. These exist only when the coil is in motion. Friction. Although the coil is normally very lightweight, the pointed ends of the pivots have extremely small areas, so the surface load per unit area can be considerable. In some cases the bearings may be broken by the shock of an instrument being slammed down heavily upon a bench. Some jewel bearings are spring supported, as illustrated, to absorb such shocks more easily. The taut band method shown in Figure 3-3b is much tougher than jeweled bearing. Suspension. As illustrated, two flat metal ribbons, phosphor bronze or platinum alloy, are 32. Electromechanical instruments chap. 3-pointer. Coil. Spring supported. Jewel bearing. Pivot. Jewel bearing. A. Pivot and jewel bearing suspension. Pointer. Coil. Spring taut band spring. Taut band suspension. Figure 3-3. The moving coil in a PMMC instrument may be supported by pivots in jeweled bearings, or by two fiat metal ribbons held taut by springs. Taut band suspension is the toughest and the most sensitive of the two. Held under tension by springs to support the coil. Because of the springs, the metal ribbons behave like rubber under tension. The ribbons also exert a controlling force as they twist, and they can be used as electrical connections to the moving chill. Because there is less friction, taut band instruments can be much more sensitive than the jeweled bearing type. The MOT sensitive jeweled bearing instruments give full-scale deflection, FSD, with a coil current of 25 A. With taut band suspension, FSD may be achieved with as little as 2 A of coil current. The fact that the spring-mounted ribbon behaves as a rubber band makes the instrument extremely rugged compared to a jeweled bearing instrument. If a jeweled bearing instrument is dropped to a concrete floor from bench height, the bearings will almost certainly be shattered. A taut band instrument is unlikely to be affected by a similar fall. Seconds. 3-to-1 permanent magnet moving coil instrument. 33 PMMC construction. Details of the construction of a PMMC instrument or D'Arsonval instrument are illustrated in Figure 3-4. The main feature is a permanent magnet with two soft iron pole shoes. A cylindrical soft iron core is positioned between the shoes so that only very narrow as possible in order to have the strongest possible level of magnetic flux crossing the gaps. The instrument scale. Another detail shown in Figure 3-4 is one of, usually, 2 or 3 counterweights. Attached to the pointer, this is simply a machine screw along which a small screw threaded weight can be adjusted. The counterweights provide correct mechanical balance of the moving system so that there is ND gravitational effect on the accuracy of the instrument. The PMMC instrument in Figure 3-5 illustrates a different type of construction. Instead of using a horseshoe-shaped permanent magnet, the permanent magnet is placed inside the coil, i.e., it replaces the soft iron core shown in Figure 3-4. A thick cylindrical piece of soft iron surrounds the coil and the magnet. The magnetic flux flows across the air gaps and through the soft iron, and the coil sides move within the narrow air gaps. A permanent magnet. 0. Control. Pole snow. AI air bap gay pole shoe. Figure 3-4. A typical PMMC instrument is coil soft iron core counwale NE, coil constructed pole that shoes, moves A of soft iron in horseshoe the air core, gap magnet, and between a suspended soft iron the core and the pole shoes. 34 Electromechanical Instruments Chap. 3 Soft iron. Cylinder. Permanent. Magnet. Permanent. Magnet. Soft iron. Cylinder. Figure 3-5. In a core magnet PMMC instrument, the permanent magnet is located inside the moving coil, and the coil and magnet are positioned inside a soft iron cylinder. Major advantage of this core magnet type of construction is that the moving coil is shielded from external magnetic fields due to the presence of the soft iron cylinder. The current in the coil of a PMMC instrument must flow in one particular direction. To cause the pointer to move, positively, from the zero position over the scale. When the current is reversed, the interaction of the magnetic flux from the coil with that of the permanent magnet causes the coil to rotate in the opposite direction, and the pointer is deflected to the left of zero, i.e., off scale. The terminals of a PMMC instrument are identified as plus and to indicate the correct polarity for connection, and the instrument is said to be polarized. Because it is polarized, the PMMC instrument cannot be used directly to measure alternating current, sent without rectifiers. It is purely an instrument. Torque equation and scale. When a current flows through a one-turn coil situated in a magnetic field, a force F is exerted on each side of the coil. Figure 3-6, A. F equals BL newtons, where B is the magnetic flux density in Tesla, J is the current in amperes, and slash is the length of the coil in meters. Since the force acts on each side of the coil, the total force for a coil of N turns is F equals 2 BIIN newtons. The force on each side acts at a radius r, producing a deflecting torque. Tp equals 2 BUINR Newton meters, N, M. Equals Blun, 2R. Tp equals blind, 3 to 1. Where dis the coil diameter figure 3-6, B. Seconds. 3 to 1 permanent magnet moving coil instrument 35, A. Force F acts on each, B. area enclosed by side of the coil coiles dx cent. Ma. 46. 28. 010. C. Linear scale ONA. PMMC instrument. Figure 3-6. The deflecting torque on the coil of a PMMC instrument is directly proportional to the magnetic flux density, the coil dimensions, and the coil current. This gives the instrument a linear scale. The controlling torque exerted by the spiral springs is directly proportional to the deformation or wind-up of the springs. Thus, the controlling torque is proportional to the actual angle of deflection of the pointer. Tc equals Ko, where K is a constant. For a given deflection, the controlling and deflecting torques are equal. K at equals bind. Since all quantities except at and/r are constant for any given instrument, the deflection angle is at equals Cl. 3 to 2. Where C is a constant. 36 Electromechanical Instruments Chap. 3 Equation 3 to 2 shows that the pointer deflection is always proportional to the coil current. Consequently, the scale of the instrument is linear, or uniformly divided, that is, if 1 Ma produces a 1 cm movement of the pointer from 0, 2 Ma produces a 2 cm movement, and so on. See figure 3-6, C. As will be explained, the PMMC instrument can be used as a devoltmeter, a DC ammeter, and an ohm meter. When connected with rectifiers and transformers, it can also be employed to measure alternating voltage and current. Copyright Jame 3 to 1. A PMMC instrument with a 0.100 turn coil has a magnetic flux density in its air gaps of B equals 0.2 T. The coil dimensions are D equals 1 cm and / equals 1.5 cm. Calculate the torque on the coil for a current of 1 Ma. Solution equation 3 to 1. Tp equals bind equals 0.2 Tx 15x10 x1 Ma x 100 1 x 107 equals 3x 10 degree nm.